In this lesson, you will learn how to use integration by parts. Integration by parts is used when you have a product, a quotient, or a chain rule, and U-substitution fails. So if we first look at number 1, before we look at the integration by parts formula, we have the integral of x times e to the 2x. The two functions that I have that are being multiplied together are x and e to the 2x. So you want to make one of these functions your u, and the other one you want to make dv. Now the question is, which one do you make u and which one do you make dv? So I'm going to start by letting u equal x, because when I find the derivative of u, which is du, I'm left with 1 dx. So I've made this function simpler. So since I made my u x, then I have to make dv equal to everything else that's left in the problem, including the dx. So dv is equal to e to the 2x dx, and now going backwards to find v, I would integrate e to the 2x dx, and that would give me e to the 2x over 2. So now looking at the integration by parts formula, I've identified u and I've identified dv. So now I look at the right side of the formula and I substitute in u times v minus the integral of v du. So u is x, v is e to the 2x over 2, and then minus the integral of v e to the 2x over 2, and then du is just 1 dx or dx, and I'm going to write this first part here, this uv, as one fraction, x times e to the 2x over 2, and then I'm going to take out the constant of 1/2 in the integral. So the goal of using integration by parts is to get this integral part in a way that can be integrated. And with only the integral of e to the 2x dx, it's now a simple integral to integrate, so that I have x e to the 2x over 2 minus 1/2 e to the 2x over 2, so that my final answer is x e to the 2x over 2 minus e to the 2x over 4 plus c. First, for number 2, I'm just going to write the formula down again. The integral of u dv equals u times v minus the integral of v du. So for this problem, there is not a u substitution that I could make so that I could integrate the integral of the natural log of x. So that's where I'll try integration by parts. But this integral, it seems as though that there is only one function, the natural log of x. But there are actually two. It's the natural log of x, and then dx is separate. So I'm going to start by letting u equal the natural log of x, because when I find du, I'm now left with 1 over x dx, so that my dv is equal to dx, and then when I integrate dx, I get x. So now that I have all of my parts labeled, I have my u, du, dv, and v, I'm going to substitute them into the integration by parts formula, and hopefully this part of the formula will be something that can be integrated. So I have u is natural log of x times v, and then minus the integral of v du, so x times 1 over x dx is x times the natural log of x minus the integral of just dx. And when we integrate dx, we just get x, so our final answer is x times the natural log of x minus x plus c. For number 3, before I start identifying my u and my dv, I want to rewrite this integral so that you can clearly see the two separate functions. The two separate functions are the natural log of x and 1 over x squared dx. Be careful that you don't just look at this as the natural log of x as one function and x squared as the other. You want to look at it as an entire function, which would be 1 over x squared. So one of these functions will be u, the other function will be dv. And usually when I see a natural log, I usually start with that being u because it's easy to take the derivative of. So u is equal to the natural log of x, and then du is equal to 1 over x times dx. So then if I let dv equal what's left, which is 1 over x squared times dx, and when I integrate 1 over x squared dx, I get v to equal negative 1 over x. And now if I substitute these four expressions into the integration by parts formula, starting with u times v, I have the natural log of x times negative 1 over x, and then minus v du, which is the integral of negative 1 over x times 1 over x dx. And then I can write this as negative natural log of x over x, and the two negatives change to positive 1 over x squared dx. And now this integral is something that is easy to integrate, which means that integration by parts worked. And when I integrate this, I'm left with negative 1 over x, and since this is an indefinite integral, I want to add c. For number 4, my two functions are 2x and the natural log of x plus 1. So just as we've been seeing with the last few problems, I'm going to start with u equal to the natural log of x plus 1. And du is equal to 1 over x plus 1. So that dv is equal to 2x dx. And then when I integrate, I get 2x squared over 2, which is just equal to x squared. So starting with u times v, I have the natural log of x plus 1 times x squared, and then minus the integral of v du is x squared times 1 over x plus 1 dx. And if I rewrite this as x squared times the natural log of x plus 1 minus the integral, I'll now combine this as one fraction, x squared over x plus 1 dx. So once again, we use integration by parts when U-substitution fails. And what integration by parts is supposed to do is give us an integral that can easily be integrated. But what happened when we did integration by parts, it turns out that we have an integral that can't be integrated in the way that it is written. So when you have an integral where you have a quotient or a rational function, and the degree of the numerator is greater than or equal to the denominator, you want to use long division to rewrite the fraction. So on the side here, I'm just going to take x plus 1 and divide it into x squared. It doesn't mean that integration by parts failed. There are just some extra algebraic techniques that we have to do to finish the problem. So if I take x and divide it into x squared, I get x. Now this x gets distributed to both of these terms so that I have x squared plus x, and the rule for long division is to subtract, and so my signs change. This cancels, and I'm left with negative x. So now x divides into negative x, negative 1, so that I have negative x minus 1. And now when I subtract, the signs change, and I'm left with just 1, so that I can rewrite this function as x minus 1 plus the remainder of 1 over x plus 1. So rewriting the first part, x squared times the natural log of x plus 1, and then the integral is now x minus 1 plus 1 over x plus 1. The only thing that's left to do is to use a U-substitution for the x plus 1. So this problem actually had 3 techniques: integration by parts, long division, and now U-substitution for the 1 over x plus 1 term. So one thing that you might find easier is if I separate this integral into 2 integrals, since part of it does not require a U-substitution, but one part of it does. Also, you have this minus sign on the outside, so I'm going to use brackets. So I'll be integrating x minus 1 dx, and then plus the integral of 1 over x plus 1 dx, and I'll let u equal x plus 1 and du equal dx. And I'll integrate after I substitute in the U-substitution. So that I get x squared over 2, and then just be careful with this negative, it's distributing, so it's changing the signs, and then plus x, and then minus the natural log of the absolute value of u, and then we have x squared times the natural log of x plus 1 minus x squared over 2 plus x minus the natural log of u, and u is the absolute value of x plus 1, and then plus a constant. So for number 5, we have our first definite integral. And I'm going to start with u equal to the natural log of the cosine of x. So that when I find du, it's 1 over the cosine of x, and then multiplied by the derivative of cosine is minus sine, and then minus sine over cosine is minus tangent, and then we include the dx. So this was my u, which makes this secant squared x dx my dv, but I have to include the dx with it. And this is a very good dv function to have because secant squared is the derivative of tangent, so my v is just tangent x. So now that I have all of the parts identified for integration by parts, I substitute them in the formula. So I have u times v, the natural log of cosine x, times tangent x, and then minus v du, which would be the integral of tangent x times negative tangent x dx. And this is a definite integral, so I have to include 0 to pi over 6. And I can change this to a plus sign. The two negatives cancel. And then I also have tangent times tangent is tangent squared. So keep in mind that integration by parts is supposed to turn this into something that can be integrated. But tangent squared x cannot be integrated. What can be integrated, though, is an identity formula from the Pythagorean identities. Tangent squared x plus 1 is equal to secant squared x. So if I solve for tangent squared x, I get secant squared x minus 1, and now I can just substitute secant squared x minus 1 into the integral and integrate that instead. So sometimes you have to do a little bit more than just the basic integration by parts formula. So the first part is just tangent x times the natural log of the cosine of x. And then when I integrate secant squared is the derivative of tangent, and then minus 1 integrates just to minus x. So since this started out as a definite integral, I have to substitute 0 and pi over 6 into the entire expression, u times v included. So when I take pi over 6, the tan of pi over 6 is 1 over the square root of 3 times the natural log of pi over 6 of the cosine of pi over 6 is square root of 3 over 2 plus tan of pi over 6 is 1 over the square root of 3 minus pi over 6. And now we subtract 0. Tan of 0 is 0. And then the cosine of 0 is 1. So we have the natural log of 1, which is just 0. And plus the tan of 0 is 0 minus 0. So this whole second group of parentheses just cancels out. And now we just want to combine the terms in the first group of parentheses. And 1 over the square root of 3 is the same as the square root of 3 over 3 times the natural log of the square root of 3 over 2, and then plus the square root of 3 over 3, and then minus pi over 6. So the only thing left that you could do is get a common denominator of 6. So we could write this as 2 square root of 3 times the natural log of the square root of 3 over 2 plus 2 square root of 3 minus pi, and the whole thing is over 6. For number 6, we have another definite integral, the integral of x squared times the sine of x. So as we work through this problem, you're going to see that this one is a little bit different than the first 5 that we've already seen. But when you first look at this, you can easily identify your two functions as x squared and sine x. So I like to pick my u to be the one that is simpler when I take the derivative, which would definitely be x squared. Because when I find du, it's now only 2x dx. My dv is equal to sine x, but I have to include the dx with it. So I have sine x dx, and sine x is the derivative of minus cosine. So when I substitute this in to the integration by parts formula, I have u times v, so x squared times negative cosine x, and then minus v du. V is negative cosine x times 2x dx, so that when I make this simpler, I have negative x squared cosine x plus, take out the constant of 2, and I have x times cosine x dx. So when I look at what's left in my integral, I have x times cosine x dx, which can't be integrated, so I'm still left with a product. So in an example like this, I have to use integration by parts again. But this time, when I pick my u to be just the variable x, my du is just dx. So I won't have to use integration by parts a third time. My dv is equal to cosine x dx, and v is equal to sine x. So when I write this out, I have to keep that minus x squared cosine x, that was my original u times v, and then plus 2, and now the purple u's, v's, du's, and dv's get substituted into the integration by parts formula again. So now I have a new u times v, x times the sine of x, and then minus v du is the integral of sine x dx. And keep in mind that this is a definite integral, so we have to include 0 to pi. And looking at our integral, we just have sine x. That's something that can be integrated. So I don't need to use integration by parts again. So when I integrate sine x, negative cosine is the integral of sine x, but then I have this minus in front, so it's going to be plus 2 cosine x. And into the entire expression, I substitute in pi and then 0. So starting with pi, I have minus pi squared times cosine pi is negative 1, and then plus 2 pi times the sine of pi is 0, and then cosine of pi is negative 1, and we want to subtract 0, which is giving us 0, and then plus 0, and then plus 2 times the cosine of 0 is just 1. So we have pi squared minus 2 is pi squared minus 4. For number 7, we have the integral of e to the x times sine x from 0 to pi. This problem has two functions, e to the x and sine x. The problem with this example is that if I let my u equal to e to the x, then my du is equal to e to the x dx. Well, that does not make the problem simpler. We're trying to pick a u so that when we take the derivative of it, it's a simpler function. So it would seem like this is wrong. So if I had let my u equal to sine x instead, then my du would be equal to cosine x dx, but that doesn't seem to be making the problem simpler either. So it would seem like integration by parts fails, but it actually doesn't fail. What you want to do with this problem then is to let your u equal whichever function you want. And I'm just going to pick u to be e to the x. So then du is e to the x dx, dv is sine x dx, and v is equal to negative cosine x, because the derivative of negative cosine x is sine x. So when it looks like integration by parts is failing because your du is not made simpler by either function, just pick either one of them for your u. And when you substitute it in the formula for integration by parts, we have u times v, e to the x times negative cosine x, and then minus v du, or the integral of v du, is negative cosine x, and then e to the x dx. And not only am I going to rewrite what I just wrote in red, but I'm also going to rewrite the original integral. And I'm doing this because finding a du did not make the problem simpler. That's how you know to rewrite the original integral. And then I simplify what's on the right side of the equal sign, minus e to the x cosine x, and then plus the integral of e to the x cosine x dx. So it seems as though integration by parts did not help, but I'm going to pick u equal to e to the x again, du equal to e to the x dx, and then dv equal to cosine x dx, so that v is equal to sine x. So I'm going to rewrite this whole problem, substituting all of this here back into the integration by parts formula. So we have the integral from 0 to pi of e to the x sine x dx equals minus e to the x cosine x, and then plus we have u times v, e to the x times sine x, and then minus v du, so the integral of e to the x sine x dx. And don't forget that we're integrating from 0 to pi. So it looks like we went in a big circle and we just created the original integral that we started with. And we actually did go in a circle. But now this actually can be integrated, because if I add this integral to the left side of the equation, it cancels, and I have two of these same integrals, so it's 2 times the integral of 0 to pi of e to the x sine x dx equals negative e to the x cosine x plus e to the x sine x. And what I've done is I've isolated the integral that I was trying to integrate from the beginning, but I just have to divide everything by 2 so that these cancel. And I have the integral from 0 to pi of e to the x sine x dx equals negative e to the x cosine x plus e to the x sine x over 2 and now I just have to substitute in pi and 0. So I have negative e to the pi times cosine pi is negative 1 plus e to the pi times the sine of pi is 0 and then over 2 and then minus negative e to the 0 is negative 1, cosine of 0 is 1 plus e to the 0 is 1 times the sine of 0 is 0, so that I have e to the pi over 2 and then plus 1 over 2 is equal to e to the pi plus 1 over 2.